Alright guys, welcome to my next tutorial. Today we shall be looking at binary knapsack. Uh, there are various variants of the knapsack problem. One of them is the binary knapsack. We'll look at that with an illustration. Let's consider this example whereby we have this following instance consisting of two items. Item 1, the first item has weight 1 with value 2. The second item has weight 10 with value 10. And the weight capacity is 10. So what the binary knapsack is saying is you have like a box, and which you call the knapsack. You want to pack as many items as possible into this knapsack. But the problem is this knapsack has a limitation. It has a limitation of the weight that it can carry, and that is what we call the capacity or the weight band. So you can only carry the number of items whose weight is less or equals to the capacity. So that's the restriction. So how can we carry as many items as possible in order for us to maximize the value? The value is just like saying maybe the currency amount, maybe the currency that we can get. So like in this case, item 1 has a value of 2, and item 2 has a value of 10. Definitely item 2 has higher value than item 1. So now in binary knapsack is 0 or 1. We refer it to 0 or 1. So in binary knapsack you can have, is either you carry an item or you don't carry it. That's the meaning of the binary, 0 or 1. So if you carry the item, that is 1. If you don't carry the item, that is 0. So it's either you carry or you don't carry it. Even with the binary knapsack, we still have two variants of binary knapsack. We have the multiple, where the no multiple, where you can have multiple. And what this is saying is, even though this is binary, you can carry the item or you may not carry it. It's saying that in no multiple, it means you can only carry one item once. Once you have carried the item, you cannot carry the item the second time. The multiple case is saying that you can carry an item as many times as possible. So that's the difference. Then we also have another variant of the knapsack problem, which is fractional knapsack. And as you can guess, the fraction means you have a ratio. That means you can carry a percentage of the item. That is, if you have an item that weighs 5, whose weight is 5, you can decide to carry and split the item into 2 and carry 2.5 of the item. So that's what the fractional knapsack is saying. And we also have a variant of that where you have no multiple, and what that means is that the item that you are carrying, if you are taking that item, you cannot take multiple of that item. That is, once you have taken an item once, you cannot take it again. Alright, and multiple means you can take that same items many times as possible. So let's look at how we can go about this using this instance. So now I've represented here in a table as item A and B. Now there are many approaches to the knapsack problem. The reason is the knapsack problem is NP hard. This problem is NP hard, and what it means that it's a difficult problem. The problem is intractable. The problem is intractable. And so because it's NP hard, we need to look for a kind of approximation algorithm to be able to allow us to get the best that we can get from solving this problem. Okay, so there are many approaches to which we can use to solve this problem to be able to get as optimal as possible, as optimal solution as possible, as close to optimal as possible. So, and one of them is the greedy algorithm. The greedy algorithm, whereby you take the most precious. You take the most precious. So to be able to calculate the most precious, you divide the value by the weight of each item that are available. Okay, so for instance, here to get the most precious, you divide the value by the weight. This gives us 2 over 1, which is 2, and this gives us 10 over 10, which is 1. So that is one approach. There are other approaches. There's another approach whereby you take the most valuable items first. The most valuable items, that means you look here, 2, 10, you take the most valuable, which is 10. There's another approach which says you take the least weight item first. The least weight item first, then that means here 1 and 10, the least weight is 1. So there are many approaches. But here we want to look at the most precious greedy algorithm, the greedy approach strategy here. So how does this work? Now, this strategy says that after you have gotten the ratio, you take the one that has the highest ratio. The item that has the highest ratio is the most precious. So in this case, that is item A. Item A with the ratio 2 will be taken. So, and if you are looking at the binary knapsack, the variant of no multiple, where you have no multiple, what it means is that you are taking the most precious first, and once you take this most precious, first, you get a value of 2 now, and it has a weight of 1. Since your capacity of the knapsack is 10, then you have to take away the weight of the first item that you have already taken. You take it away from the capacity of your knapsack, and then you have 9. So you have 9 more available space to fill with items. Now, since you are not taking multiple, we are considering no multiple. Since you are not taking multiple, then what that means is that you can't take item A again. You have taken it the first time, you can't take it again. So the next is for you to go to item B. Now, for you to take item B, your weight must be equals to 10, because the weight of item B is 10. And remember that we are considering binary, which means that we cannot break this item into fractions. Is it that we take it or we don't take it? Is it that we take it as a whole or we don't take it at all? So we can't take a fraction, we can't take a portion of it. So because of that constraint, these remaining spaces that we have, which is 9, becomes a waste. So what we can have in this instance is our approach, our approximation approach, our greedy approach represented with RA can only give us maximum of 2 units of value, but clearly we can see that what should have been what we should have taken, which is the optimal approach, is 10. The best that we could have gotten is 10. So if you calculate the approximation ratio, which is the ratio of the optima to the strategy, this gives us 10 over 2, and this is 5. So our approximation ratio for this strategy in this instance is 5. So this shows that the most precious strategy, this strategy of taking the most precious, is very, very bad. This is very, very bad. It's very, very bad because if you look at this approximation ratio can tend to infinity as the second items increases in value and weight. For instance, you see here that if we decide that our weight is equals to, decide that the weight is equals to n, the weight is n, and we make the value of item B to be n, and we make the weight also to be n. This is still going to give us the most precious ratio as 1, because n divided by n is 1, and we're still going to be taking the first item, item A, in this strategy, which will give us 2, which means that we'll be left with n minus 1. So what it means is that as our n tends to infinity, this is approximately n. So if n is infinity, so this will also be infinity, and that means the approximation ratio is very, very bad. Most times we try as much as possible to get approximation ratio that is within the maximum of 2, so that at least if we cannot get the exact optimal solution, we don't want our approximation to be, the ratio to be more than 2. Here we already have 5, and we can get infinity. So in this case, this algorithm, this strategy performs very badly. Let's look at case 2 using the same instance. Here we can take multiple. Because we can take multiple, it then means that item A, if we take it the first time, it gives us a value of 2, and we have weight 1 for it. So that means we can take it again the second time, it gives us a value of 4, then we have remaining weight to be 8. We can take it the third time, it gives us a value of 6, then we have remaining weight to be 7. So because we are able to take multiples, in this instance you will discover that our approximation strategy is going to give us 20 units of value, and which coincides with the optima, because what is optimal is just for us to take 10 units of item A. If we take 10 units of item A, then we are going to have 20 as our value, and our weight will be 10, which maximizes our weight, which is 10. Alright, so in this case we say that our strategy is optimal because the approximation ratio is 1. So this is optimal. Our R of A is optimal. Now I leave you as an exercise to do the fractional knapsack for no multiple and fractional knapsack for multiple on this same problem. You can put your comment below. We'll look at it, then we'll discuss it. Thank you very much for listening. If you like this tutorial, please give us a like, and if you don't like anything in it, give us if you're not okay with it, give us a dislike. All this will help us to be able to improve on our subsequent series. Thank you.